through 5th grades will design and build an elevated bridge, while 6th through 8th grades will again design and build suspension bridges. Before we build, we will have the pleasure of meeting 2 engineers from Skanska, a world-leading project development and construction group. Mr. John Schroerlucke and Mr. Bob Walent will tell us about an amazing bridge that they are working on. I'm sure you'll be able to use some of the concepts they will talk about in your design. After they speak, we will have a few moments for questions and answers. When you start building, our engineers and residents will visit classrooms to chat with you as you build. So please help me welcome Mr. Schroerlucke and Mr. Walent.
Hi, good morning everyone. Thank you all for having us here. I'm John and this is Bob walking away here. We're together, we work for a company that was mentioned called Skanska, and we have the pleasure of building a very unique and landmark project in downtown Los Angeles. The bridge is depicted here. This is a computer model of what the bridge will look like when it's completed. It's flying. It goes between, I don't know if the younger crowd knows, but parents may be familiar with the Los Angeles River. Does this thing have a pointer on it? Oh, not like that. Right. So this is the Los Angeles River that flows through, and downtown LA is the buildings over on this side. This is East Los Angeles, to the east side of the bridge. Architect named Michael Maltzin designed this structure. It's made of 20 different arches. The type of structure here is called a tied network arch. So it has several crisscrossing cables. Like the older students who are building the suspension bridge, you may be trying to work with cables and getting your cables to hang your deck. This bridge works similar, that it hangs the deck below these arches. And it's a continuous 3,000 foot long structure that will connect the East LA to downtown Los Angeles. The history of the bridge, so the bridge was, the first bridge that was there was constructed in 1932. It's known, the architecture that's famous about it are these 2 center steel arches that go over the Los Angeles River. It's in movies like Terminator, the movie Terminator, some of the older movies, you younger guys probably don't know about it, but maybe you know Grease. I know you guys do a lot of singing, so if you like to sing, you should watch the movie Grease. And Grease, in the final scene, there's a car race down through the LA River. Well, the car race starts under the 6th Street Viaduct. This is early construction back in the 30s of the bridge being erected, the steel arches being erected. This is what the bridge looked like when it was first built. This is the LA River. It's much different now. This is just like a natural channel that used to flood and wash out. And so over the course of years, they constructed concrete lining in the LA River. A lot of railroad that runs through here. This is a very busy corridor in Los Angeles. The bridge, however, has, concrete, as the water mixes with the cement, becomes harder and harder and harder and turns into like a rock-like structure. Inside the rocks, there's also cement and water and little rocks. Inside the rocks, there was a material that started to have a chemical reaction with the cement, and it produced a gel-like substance that sucked up all the free water in the cement, and it expanded, and it caused the bridge to crack. You can see a little bit of the cracking. I don't know if it's clear to you all, but there's little lines. So the bridge cracked and cracked and cracked, couldn't be repaired, and so the city of Los Angeles decided to demolish the structure. So we demolished the old 6th Street Viaduct and getting ready to replace it with this new fancy bridge. So we rebuilt, so as a civil engineer, we do the bridge work, right? A lot of structure work. We also improve roads. So on this job, we improved all the nearby roads and intersections and signals and pedestrian walkways and pedestrian signals to make it safer while we take this bridge out of commission to have the people in the area be able to drive and walk around safely through the city to get around the bridge as it's closed. We do demolition of buildings, so we demolished a lot of buildings to clear the way for the new bridge. We relocate a lot of electrical power lines, so there were some electrical power lines in the way that we need to move underground. We drilled a tunnel in one section to put some power underneath the river. Other locations will just relocate all the overhead power lines you see. We'll get those out of the way. And we demolished, like I mentioned, the existing bridge, and then we'll construct the new bridge, 3,000 feet, 100 feet wide, 20 arches. So the bridge down below the ground is this circle here looks about, this is almost 10 foot, that's a little bigger. But the foundation, so underneath every one of these columns here, there's a foundation that's approximately this big. What else I have here? So that's the piles. There's isolation bearings, so we live in earthquake country, right? We haven't had one in a long time, that's good. But this bridge is designed to withstand earthquakes, and it can, these bearings, they can displace up to 42 inches. So this whole bridge, this deck system is one continuous deck. There's no joints in the deck, and it floats essentially on these isolation bearings that are 7 feet diameter. So again, pretty big. More like this inner circle here is about 42 inches. So the sliders can move, and the bridge can displace back and forth, forward, backward, when the earthquake starts to shake, and it'll protect the structure from any damage. There's a total of approximately 400 cables in this bridge. Cubic yard is, let's say, cubic yard of concrete. So we measure all our concrete cubic yard. A cubic yard is 3 feet by 3 feet by 3 feet. Yeah, about this much concrete. There's 54,000 cubic yards in this structure. Compared to the original structure was 100,000 cubic yards. So this structure is much more efficient than the old structure. There's some pedestrian ramps and some other stairways and stuff to lead you up and down off the bridge. So these are some pictures of demolition. This is us hoisting down the old steel structure. This is a plan that's developed that shows the bridge. This is what we build from, these drawings. Engineers create, they put drawings together for the builders to go constructing the structure. The architect built this model to show everybody what it would look like. So the architects build this first to give a good visual of what will happen. These are the different elements of a tied network arch. So a tied network arch, obviously there's an arch. There's an edge girder below the arch. There's beams that connect between the two edge girders to support the deck surface. And there's cables that come down from the arch to hold on to the edge girder to support the composite deck structure. So here's some other views. Let's see. These are the piles that I was mentioning. This is the drill rigs, some pictures from construction, us building the foundations, the big circle, 160 feet deep. This is one of the columns. This here is one of the bearing devices that I was talking about that are installed for seismic. What's that one?
We're talking about.
Oh, there's a little video, I think, that's showing how the bearings work. So this is a test We have to test all the bearings, make sure that they function properly. So this isn't a test apparatus. And it's displacing the bearing off to the side after it applies load to see if there's any damage to the surfaces of the bearing. The bearings are manufactured up in Mare Island near San Francisco and shipped down to the job. We set them into the columns right here at this location, and we install some big steel lockup devices so that we prevent it from moving while we build the bridge. So we got to keep everything stable so it doesn't start falling down on us as we construct, and all our builders are under the weight of the bridge as it's going up. So here's one of our Y-bent or Y columns, and this is all of our temporary false work and form work that'll go up to pour concrete inside. So inside this concrete there's a lot of steel rebar, so we reinforce all the concrete with rebar, make a form or like a mold, and we pour the concrete down inside here to fill it up and make a shape like this Y. This is the LA River during construction, one of the Y columns there at the LA River. This is where the old bridge used to cross, where I showed you those two steel arches before. So we use a lot of computer models to show us what the geometry looks like and do our structural analysis. So all these models we developed. And this is the concrete after we stripped the mold off or the formwork off. But this is the same road that was depicted here in that graphic. So we also model in our computer, we model all of the pieces of rebar and all the components of the bridge to make sure that they'll all fit together properly and to help us dimension things and build it properly. And we design all the temporary structures and all the concrete forms. So these are some drawings of the design we have here that's built to help mold and form the concrete. Another view of some of the rebar that goes inside. Here's two of the Ys that will support the bridge. Here's a picture of the intermediate. These are all the different components. So the edge girders that support the bridge from the cables will tie into this edge girder, and these intermediate floor beams will support the deck, so the cars will drive here. So there's some more forms of us forming floor beams and looking toward downtown Los Angeles. This is our design for how we're going to construct the arches. So here's the arch, this is the model again. So this is the design of how we're going to construct from the deck up and build this arch structure and install these cables. Bob, do you want to talk about hangers? This is Bob Walent from New Jersey. We brought him out here to California because he's an expert in cables and suspension bridges.
Morning. So as John was saying, this is the network cable arch. As you can see, all these cables are in a cross pattern, a diamond pattern here. And here, these are just two different types of spans that we have. Again, there's 10 different spans. And there's difference in the height of the arches here and there, as you can see. And the way the cables are attached is you have the upper arch, which is concrete. You have the bottom edge girder that John talked about, also concrete. And then connecting the two are steel cables here and steel plates. And there's adjustments on these things right here. So know, they've taken actually look just like that. So prior to what John was talking about, all the false work that's underneath the structure holding everything up, we put all these cables in, and those are actually what they look like. We're going to take them, put them in there, we take and adjust them right here. We're going to take the jacket together, put the tension into them, adjust them, and then we can release the false work. And now the cables are what's going to be holding up the bridge instead of supports from underneath. So there's a couple types of arches. There's what they call the tide arch, which is above. There's a couple different types. There's the network, which we are building. The network arch, what we're building, it's a more efficient type of arch. It has what they call redundancy. As you can see, there's a number of cables all the way through. When you put a load over here, it transfers up on an angle to part of the arch. It makes it a lot more efficient than having the hangers vertical like you see here. The tide arch also has a bottom cord that comes across here, the edge girder or the deck, and that's actually pulling the two parts of the arch together, holding it from breaking apart, collapsing. So you have that. There's another type of arch called a thrust arch, which a lot of, I don't know how many people are familiar with the Sydney Arch down in Australia, but it looks very similar to this. This happens to be the Payoff Bridge that Skanska is currently building or renovating in New Jersey and New York. It pushes it down on either side, so there's nothing pulling the arch together. It's pushing down on the ground. And this happens to be one of them where, again, we're doing this job. The roadway was originally here, and we're raising it up 60 feet in the air. We raised it up 60 feet in the air while we kept traffic on the bridge and boats coming underneath it. So if anybody's familiar around here with the Gerald Desmond Bridge that they're putting in, the new one there, they're bringing that up about 60 feet in the air. That was the same thing we did here, except, well, we didn't take the old bridge out of service. We actually used the old bridge to build a new roadway on top of it. So that was a bit of a challenge there. So again, we're building a tide arch bridge, network tide arch down at 6th Street. But today, you're going to be looking at doing a suspension bridge. So what is the difference between them? Well, we're going to do a little cartoon here, going from an arch bridge to a suspension bridge. Hopefully it works. Drop each piece out. So basically, where what you're building today with the suspension bridge, the cable itself that's holding up the bridge is in tension. You turn that upside down, it becomes in compression. It turns into an arch. And you just use different materials, but the concept behind supporting the structure is basically the same.